Hi everyone, welcome to the first video on my series about fine-tuning large language models. In this video, I'm going to fine-tune LLaMA 3.2 1 billion parameters model on a Python dataset. To start, you will need to install the necessary requirements. So here, under this folder, I create a text file called requirement.txt. In this text file, I list out all the necessary package that is needed for this project. So here note that I am creating this project on a cloud, and the website that I subscribe to is Paperspace. So because I need to use some GPU, I need to subscribe to some cloud service. So going back to the instrument, we need dataset, we need TRL, which is the short form for transformer reinforcement learning. I'm not quite sure about this. PEF is a parameter efficient fine tuning. So we need these three packages, and we also need bits and bytes. So you need to install this to start. And in order to use LLaMA model from Meta, you will first need to go to Meta LLaMA from Hugging Face. Go here, agree to their terms and agreement. It should be down below. If you haven't done so, you need to click agree to their terms. Only by doing that, you will be allowed the access to use the model. You also need Hugging Face access token. To get a Hugging Face access token, you can do so by clicking on your icon on the top, click setting, and under setting go to access token. You need to create a token with read permission. Note that you need to read permission tokens. So here I already have one. If you don't have one, just click here and create a token with read permissions. Once you create such a token, you should download the CSV file and save the token in your local computer. The way that I do it is I save this token in this it's a JSON file here. So I save it and I simply read the access token from this JSON file. So before we can load the model, we need to log in using our token. So here we can import login from Hugging Face Hub, read the config.json file, and here you can see this is just a dictionary with keyword Hugging Face access tokens. Let me go back to this. After you run this, you will log in Hugging Face. For the data set, so next we are going to process the data for the training. We will need to import load dataset and dataset from datasets. So for the data that we are using, let me show you how the data that we are using. So the data that we are using is a Python code instruction data. It has 18,000 Python problems together with solutions. Let's go to viewer to see one example. So for each sample in this data, we have keywords. Each sample is a dictionary which contain keywords, instruction, input, output, and prompt. Basically, I would use instruction, input, and output. Instruction is the instruction for the sample. In this case, create a function that can calculate the sum of a sequence of integers. The input is the input to the problem, and output is the Python code. So if you click to another example, you can see here generate a Python code for crawling a website data, a website for a specific type of data. And this is the website, and the specific type data is phone numbers, and this is the code that is used to get all the phone numbers, right? And so on. So this is a Python dataset. So by training LLaMA on this Python dataset, we expect LLaMA to be more specialized in this Python dataset, and in particular we hope that it understands Python better and able to generate or write more compelling Python codes. Now let's go back to this section about data. In order to prepare the data for the training, first we need to format each of the data sample in the format that the model expects. So here, for each sample, as I mentioned, I will focus on the 3 keywords: instruction, input, and output. The prompt here is basically the prompt that should be fed into any model. Here in this case, I will use LLaMA 3.2, so I will construct a prompt that fit the type of data that LLaMA 3.2 expects. So I define this format sample function to format a single input sample into the model. I extract the instruction, the input text, and the output text. The input text here can be none or can be an empty string. So in the case it is none or empty string, we don't need to in fact feed it into the instructions. So the formatted prompt goes as follow. We start with a start header ID for the users, and then the instruction is in the 𝗬𝗏𝗃 format. This is the standard format for instruction fine tuning. So below is an instruction that describes a task. Write a response that appropriately completes the request. We start with instructions, and this is the instruction, and we have response, and we end this request from the user with this token EOTID, is the short form for end of turn. So this is to tell the model that this is the end of turn for the user input. And we start with this actually this is the one that was not updated, so I should show you this one here, which is the recent one. This the other one just now is the former one where there is some problem. So I need to bring back your attention to this one. Basically it's still the same, right? We start with the user request, that is up to this point here, where we stop at the end of turn ID token. And for the model to start generating response, we will start with start header ID, assistant, and header ID. So this is to tell the model to start generating the response. And output text is the text that we expect the model to generate, and we end the generation with the end of turn ID. So this is the case where there is no input, which means the input is usually already provided in the instructions. For the case where there is an input, we also do the same. So here we just add an addition input to the user request, that is input. We also end the user request with the end of turn ID, and we prompt the model to start generating with this starting header, assistant, and header, and this is the text that we expect the model to output. So yeah, and we use this format and join formatted prompt here with this empty string in order to exclude all the trailing white space that might be there in the dataset. Well, next I will write a generator for the train data and the validation data. Okay. So for first, let's look at the generator for the train data. This is written in the function gen train input. This generator will format all the train data into the 𝗲𝗏𝗏 style, which is the format that you have seen. And we expect to return a generator on the train data. First, we will load the dataset using the load dataset functions. We put in the address of the data, and here it's optional to set streaming. In this case, actually, we have a quite small data. It's not necessary to set streaming equal to 2, but I just want to learn about this method. Setting streaming equal to 2 basically means we load the data one by one instead of loading the whole data all at once. So this is very useful in the case we have a very large data set, and it might not be practical to load the whole data into your computer all at once. And also, if let's say we only want to use a small fraction of the data set, it is not necessary to load the whole data all at once. In this data set, we have like 18K samples of Python codes. I would use 90% for training and 10% for validations. So here I would use this number of sample for training. So here for the sample in the iterator of dataset, I will load up to this number of samples, right? So for each sample, I will format it using the format sample functions, and then I will use this dictionary, which will be stored in the generator. So, and then increase the count. Well, I do the same for the validation data, but here I only start when the counter exceeds this number, so I can take 10% for validations. So after doing this, we will call the functions. So train dataset. Here we use the dataset method from generator, pass in the generator to get the train dataset and validation dataset. So here, let's go down and look at the number of train data, number of validation data, and also a sample. Right? So we have 16,800 train data, 1,800 validation data, and a sample train data look like this. It is a dictionary with the keyword text, and this is the content of the text. Right? So it includes both the instruction from the user and the output. The output is apart from here. And so now the data is prepared. It remains to load the model, prepare the tokenizer, and train the model. Well, as we know, this model is it has 1 billion parameters, so it is not practical to train the whole model. The technique that I am using to train this model is called LoRa, low-rank adaptations. Well, I would recommend you to in fact, if you like to really study LLM and understand the LLM, I would recommend you to go to this repository and by Sebastian. He basically code or build LLM from the scratch. This is a classic book, in my opinion. Before I have basically no confidence at all in order to dive in any LLM project. However, after finishing his book, not even finishing his book, after reading like 80% of this book and follow his code, now I have confidence to dive in LLM projects. Right? So in this book, basically he go through the creation of GPT-2 and LLaMA 3 from the scratch, and you understand every single component of it. Every single step is made crystal clear, and it is just amazing to see, to understand things. All right, so now going back to this, I will utilize auto model for causal LLM in order to load the model, auto tokenizer to load the tokenizers. Bits and byte config here is used to basically to compress the configuration for the parameters. I'm going to use the quantization type called NF4. This is a special type to reduce the model size. For the trainer, I would use SFT trainers, supervised fine tuning trainer from transformer reinforcement learning. So this is the model ID. Right? So first, we will load the model and the tokenizers. So this is the configuration for the data type. I will quantize the data to NF4, a special type that compress the data type to 4 bits. So to load the model, we will simply pass in the model name. Quantization configurations is here. The device we can set to auto. For the token, it's access token, which should be already loaded in here. Right. And here we need to set the parameters for LoRa configuration. Again, LoRa means low rank adaptations. What LoRa means? Okay, let me try to go to Sebastian post here to see whether he explain LoRa in details. LoRa layers, linear with LoRa. Okay, I need some figure. Well, all these maybe let me just go to Google. Hopefully I get some image. Okay, so here is what I want. So let's look at this image, and here on the left you have the usual linear layer, right? You have an input of dimension D. You feed through a linear layer, let's say in this case D by D, then you get the output. The number of parameters in this case will be D squared. So in LoRa, we make this original layer become a combination of two things. So we still keep the original layer, and we create an additional layer where there are two parts in this additional layer. The first linear layer here, A here, has size D by R, where R is very small compared to D. And so this is like a down projections of the input to dimension R, and B here is the up projection to the dimension D. So for this layer, the total number of parameters will be D times R plus R times D, so that is 2 times D times R. So in this case, we will replace this original layer by these two, by the addition of these two, and furthermore we will freeze the weight of this original layer and only keep this part chainable. By doing this, the number of chainable parameters is reduced significantly. Note that here, because R is much smaller compared to D, so the number of chainable parameters is reduced. Right? And we also retain this part where we freeze the weight. That means we still retain the knowledge from the original model. All right, so let me go back here. Oh, okay. I'm a bit scared because I'm still training this. You can see below here. All right, so we have set the parameter, the parameter efficient fine tuning configuration to be LoRa configurations. Well, in the configuration here, there are a few parameters that we need to set. We need to set basically alpha and R. R is the rank that we have seen just now. Right? Alpha is the weight of this size. So it is a scalar multiplication of this size. It is by an experiment that 16 and 8 are the standard numbers. Right? A dropout here is usually 0 or very close to 0. In this case, I set to 0.05. Bias is none. Task type is causal LM. So target modules here mean the modules that we target to reduce the parameters, or we target to apply this LoRa. And here I target the projection of the query key and values. So now we can load the tokenizers using the auto tokenizers, and we pass in the model name with the access tokens. We also set the pathing token to be this fine-tune drive path ID. This is a special pathing token used specifically in LLaMA 3.2. The pathing size is right size. So I will return the model, the tokenizer, together with this LoRa configuration. So after this, I get the model, the configuration, and the tokenizers. So now comes to the training. As you see, I'm still running the training loop. So to train this, I will use the supervised fine tuning trainer from DRL, and I also use the configuration from DRL. For the configurations arguments here, we need the output directory, number of chain epochs. I should have set this to 1 instead of 3. So note that for one thing for LLM is training more epochs doesn't mean better generalizations. Training more epochs only means that the model learn better the training data. And in fact, if you set this to too large, in many cases, it might generalize worse because the model will incline too much on the chain data set. Right? In that case, it might fail to generalize to the data that it never see before. We set per device chain batch size to 16, valuation batch per device valuation batch size to 16, and we also set the gradient accumulation step to 8. So this means we only compute the backward pass every 8 batch, not 8 epoch. The forward pass is computed every single batch, but the backward pass where we need to compute the gradient is only computed every 8 steps. So after 8 steps, we will compute the gradients and update the parameters. This will make the computation faster. We set gradient checkpointing to be true. Optimization here is AWW, the fused versions. And we also set locking step equal to 50. Basically, we will log or write out the chain loss every 50 steps, every 50 batch. For evaluations, this part is in fact optional. I also don't, it's just there for us to monitor how the model perform on some data that it never see before, but for LLM I don't find it is that important, but it's still useful, so I still keep it here. We will evaluate the loss for every 50 steps on the evaluation, on the validation data. Our save strategy here is epoch, so we save the model after every epoch, and we specify some data type, and we set the gradient, max gradient to be 0.3, warm-up pressure 0.03 here, follow the 𝗬𝗟 paper. Yeah, and the rest are pretty standard. Data set text field is text, because just now you can see the text is the keyword in the output data for after we apply the format sample function. And for the trainer, we need to specify the models, the training arguments, the argument that we specify above, the train dataset, evaluation dataset, the parameter efficient fine-tuning configurations, and tokenizers. After that, we hit trainer.train. Let's see how my model is training. So under this configuration, I need to train for about 400 steps. Now I'm about halfway there, right? 190 steps. And you can see the chain loss has been decreasing. So I expect it to finish in about 40 minutes. So before I pause the video here and wait for the training to be finished, here we also want to save the model, the model static, should be static. So here there are two methods to save the model. One is this traditional method. So for this video, I will use this traditional method where we save the model in PyTorch. So we specify the model file name and just use torch.save and then save the model. So in this case, we save the whole model. But note that this will be inefficient because the whole model is quite large. Another method is to save only the part, the train part of the model, which is this part where we modify. And when we save it, this turns out to be much smaller. For this train method, I will go through it in the next video. But for this video, we will just look at this traditional method where we save basically the whole model. I will pause the video here, wait for the train to be finished, and then I will proceed with the evaluation of the train model and also inference of the train model. Now the training is complete. Let's look at the information here. So here we see that we train for 393 steps and the training loss gradually decrease. The validation loss also decrease. Next, we are going to save the train model. As I mentioned, in this way of saving the state dictionary, we are saving all the parameters, including both the trainable parameters and the original parameters. So it is not an efficient way, but for this video, as it is the first video, also the starting video in this series, I'm going to use this traditional way. So we simply call torch.save on the state dictionary of the model. And after we save it, we can free the memory by deleting both the model and the trainer. So, well, just now I already saved it and delete the model, so that's why model is not defined. but after you do this, suppose it will be safe. Next, we are going to load the fine-tuned model and run inference on the fine-tuned model. So here I will write a function to load the fine-tuned model. So I will need to import parameter efficient fine-tuning model, the configuration, LoRa configurations. From transformer, I need the auto model for causal LM and auto tokenizer. Here, first we will load the tokenizers and the base model. Right? We specify the device, load tokenizer from the base model ID, and then load the base model, move it to the device. For the LoRa configuration, make sure that these configuration match the one that you use in the training. So these need to be exactly the configuration that you used before. This is the LoRa configurations. We will need to initialize the model which use the LoRa configurations, and this is the way to do it. In this path model, we need to pass in the base model together with the LoRa configurations, and we load the safe weights. So note that these safe weights include both the fine-tuned wave for the LoRa layers and the original weights. And here, because there is a difference between the names, I need to create a new dictionary so that the name of this LoRa model match the name of the safe model, the safe dictionary. So basically, I need to add base. I need to add this subscript base to the new key for the base model. So I iterate through all the items in the safe dictionary and add this base to all the key that were saved in the state dictionary. And after that, all the names will be matched, and I simply load the parameters from the new state dictionary. After loading the parameters, I will set the model to evaluation mode, and here I return the model together with the tokenizers. Right? And to call this function, we need to specify the base model ID and the safe weights. So the base model ID is LLaMA 3.2, 1 billion parameter instruct model, and the weights is the path to the safe dictionary, state dictionary. Here we load the model, then we get the fine-tuned model and the tokenizer. Here I also print out the total number of parameters and the total number of trainable parameters. So here let's run this. Yeah, so here you can see the total number of parameters is over 1 billion. However, because we only fine-tune the LoRa layers, the total number of trainable parameters is much smaller. That is only 1 million trainable parameters. Next, we are going to generate output from the fine-tuned model. So I create these generate functions which take in the model, the prompt from the users, the tokenizers. Max new token is the maximum number of tokens we expect the model to generate. Context size is the basically the size of the context from the prompt. Temperature and top K here are parameters used in choosing the next token. The end of sentence ID here is the ID that tell the model to stop generating. So these two are EOT ID, either end of turn ID or end of text. So whenever the model sees this ID, they will stop generating. Well, first we get the expected data type of the model, and the device, right? We need to format the prompt. So note that the prompt here can be a very raw prompt from the user, so we need to format it so that the model can accept the exact type of input that it expects. So here the prompt is in the format as before. Below is an instruction that describes a task. Write response that appropriately complete the request. Then we put in the instructions. And here for the response, we will stop here. In order to prompt the model to start generating the response, we will include this part. Start header ID, assistant, and end header ID. This basically tells the model to start generating the response. We will encode this prompt using tokenizer.encode, and we will convert it to tensor. And here is the number of tokens that is going to be fed into the model. So this number of token might be large depending on your prompt. However, I set the context size to find the 12, so I will only take the last find the 12 token to fit into the model. So here we are going to generate max new tokens. So we run on this range, a for loop on this range, take the last context size tokens, feed it through the model. In fact, the model is already put to the evaluation mode. This is unnecessary. And we run the model on the input IDs, get the logics, and focus only on the last time step because we are generating token one at a time. The last time step will give us the new token. And the next part here is to apply top K filtering and temperatures in the sampling. Basically, top K filtering means we only select top K tokens from the models. The output of the model will be, if I remember correctly, it's over 100,000 tokens, which is the tokenizers used in LLaMA 3.2. Here we only select top K tokens. Top K, the default value is 1. So in the case it's 1, we will select that token. But we might set it to something which is different from 1, for example 50. Then we will select the top 50 tokens. Later we will randomly pick the token from that 50 tokens using their probability values. So we just take the top K tokens, and for the rest of the token we set the logics to -infinity, or in other words, the probability of picking the rest of the token will be 0. Temperatures is a value where we can apply in order to modify the choice for picking the top K tokens. If temperature is equal to 1, that means there is basically we keep the value the same. If the temperature is less than 1, by looking at this, you will see that it will prioritize the logics that have bigger values. Right? The bigger the logics is, then when you scale by the temperature, it will get bigger. So, and here, so temperature is a way to magnify the choice of picking the token with higher logics even more. So here you can see the next token will be picked based on the probabilities. So we check for end of sentence token if we hit the end of turn ID. So this EOS ID is either the end of turn ID, so this is the end of turn ID, or end of text. If we hit either one of these, we will stop generating. Basically, we'll break out of the for loop. We add new tokens every single step until we reach the maximum number of tokens. And after that, we will decode the generated IDs to get the text. Right? And here, note that for the generated IDs, I exclude the starting tokens, because these num tokens here is basically the formatted prompt. So I exclude this from the output. Yeah, so this is the generating function. All right, so now let's try out how this works. This is the moment of truth. Prompt here is to write a function that compute Fibonacci numbers, and let's run this. I already run it, but let's run it again. Well, so the model gives us the following output. It says this is in Python Fibonacci n, function compute the n Fibonacci number, n is the position of the Fibonacci number computed, should return the nth Fibonacci number. Base case 0, 1, 2, initialize the first two, and then we update a and b by b, and a plus b return b. Well, yeah, based on my knowledge, this is probably the best function that compute Fibonacci number in terms of time complexity and also in terms of space complexity. And this is some lead code question, easy lead code question that I just copy from the internet. Given an array of integers, return how many of them contain an even number of digits. So here, let's generate up to 512 tokens. Let's change it a little. Okay, so solution here is in Python's. So nums here is an array of integers. Right? We need to return the count of numbers with even number of digits. So initialize the count to be zeros. For each number, we will convert it to string. Right? That is a smart way. So we can count how many digits are there. So we take the length of this string, we get the number of digits. If the number of digits is even, then that number is counted and we increment the count. So we return the count. Yeah. And also it has some test case together with the explanation why this solution works. So it looks pretty good. And that is also the end of this video. In the next videos, I might dive into using a vision language model, where not only we want the large language model to understand text, we also want to have large language model understanding image. So that is the end of this video. I hope you find it useful. See you next time.